Hello, and welcome back to another IB Math speedrun with me, Vince. In today's speedrun, we're going to be going through chapter 11.1, which is all about axiomatic probability systems. So let's jump right in. So, in order to tackle chapter 11, which is of course all about probability distributions, we first need to familiarize ourselves with probability systems. So, first thing we need to know about is is a lot of set theory, actually. So for two sets, the union between two sets is equal to a set where they're containing all the elements that are part of A or all the elements that are part of B. And so on a Venn diagram, this looks like this. So if we have two sets, this will be everything containing both sets. Next, we have the intersection between two sets, which is A intersection B, and this is everything that is in both sets. So X has to be part of A, and X has to be part of B. And so on a Venn diagram, this looks something like that. So just the intersection between the two sets. So there, in set theory, we define the set U as the universal set, and so it contains every element in every other set. So this is like the entire, more or less, this U set would be the entire diagram. It's this rectangle on the outside, and so it contains everything in existence. And so if we have A union U, this is simply equal to U, and A intersection U is equal to A. There is also an empty set, which we denote as the empty set, and this contains no elements. It's equal to a length of 0. So A union with the empty set is equal to A, and the intersection between A and the empty set is nothing, since the empty set contains no elements for A to intersect with. Okay, and so now we have the opposite set. Say we have a set that's part of U. This means that it's part of the U set. So there's always a complementary set that's denoted by A prime. And so of course A prime is all of the elements that are in U but not in A. So A union A prime is equal to U, since the A prime contains all the elements of U that aren't in A, so if you union both, you end up with the original set. And A intersection with A prime is equal to the null set. Yeah. So the probability of an event happening is defined as the probability function of A is equal to the number of terms in the set of A divided by the number of terms in the set of U. So we assume that each term has an equal probability of being selected, and the sample U is all possible outcomes. So because of this, for any event, probability of A will be between 0 and 1. Since all events have a probability of occurring that's greater or equal to 0, and all of them have a probability that's greater or equal to 1. And the probability of the universal set occurring is equal to 1, since it contains all possible events that could happen. So if the probability of A is equal to 1, it is the universal set. Okay, next, if we have the probability of A union B, this is equal to the probability of A plus the probability of B minus the probability of A intersection B. And if we think about this, what this means is that this is equal to the number of terms in A union B divided by the number of terms in the universal set. Well, how do we find the number of terms in A union B? Well, the number of terms would be equal to the number of terms in A plus the number of terms in B minus the number of terms in the intersection. Since the number of terms in the intersection we need to subtract because, for example, because they would be double counted otherwise. So if we have these two sets, A and B, the number of things in A would be this red circle. The number of things in B would be this blue circle. And so in order to arrive at the union, notice we're double counting the intersection. We need to subtract this middle part. So that's why we need to subtract the intersection. Okay, so next, if an event A can occur and an event B can occur, but A and B can't both occur, then that means these events are mutually exclusive. So it looks like this. So if we have set A, set B, as you can see, there is no chance of both A and B occurring, and therefore the probability of the intersection must equal 0. So these can also be called disjoint sets. Okay, the next thing we need to know is that if we have some events A1, A2, A3, and so on, the probability of their union, A1, union A2, union A3, and so on, is equal to the probability of the first event plus the probability of the second event plus the probability of the third event, assuming these are all mutually exclusive events. So if the intersection between all these events is equal to 0, then we can get the probability of their union by simply adding up the probabilities of each event. So these things we've covered are the basis for the axiomatic probability function. And so yeah, next we need to know that next, if A is an event, if we have an event A, the probability of A is equal to 1 minus the probability of A prime, where A prime is, of course, the opposite set, the complementary set to A. And this is because the number of items in A is equal to the number of items in the union set minus the number in the universal set minus the number of items in the A prime. And so therefore it follows that probability of A is equal to 1 minus probability of A prime. And then, of course, the probability of the empty set is equal to 0, because, yeah. So, finally, and of course, yeah, probability of the empty set is 0. So, with all of this, we're now able to answer some basic probability questions. So let's jump right in. So if I can erase, that would be very nice. Yeah. Okay. So the first question that I'm gonna do, I'll just do, I guess, all the odd ones. So in a class of 20 students, 10 study French, 8 study German, and 5 study neither. Find one student is selected at random. Find the probability the selected student studies, so both French and German language, or exactly one of the two languages. So we know that we have a class of 20 students. So 10 study French, 8 study German, and 5 study neither, which means 5 study the intersection between, or actually it's equivalent to F union G outside. So in order to find the number of students that both study French and German language, we know that the number of the exclusive of F union G is equal to 5. And so therefore the number of F union G must be equal to the universal set minus this. So it's 20 minus 5 is equal to 15. So 15 students study French or German. Since this should be equal to the number of people that study French plus the number of people that study German minus the intersection between the two. Oops, sorry, you can't see that. We have that 15 is equal to 8, sorry, I think it's 10. 10 plus 8 minus the intersection. And so therefore we get the number of students that study both subjects, which is the intersection, as 3. So 3 students study both subjects. And then exactly one of the 2 languages. So wait, this is the first answer. And so to get the number that study exactly one of the 2 languages, we simply need to get we simply need to subtract this intersection again from F and G. So this, because we're getting the number from F plus the number from G minus 2 times the number from F intersection G, since this intersection would be counted twice. So this is again equal to 18 minus 6 is equal to 12 students that study exactly one of the languages. Okay, on to the next one. Next one we have there are 6 oranges and 3 kiwi fruits in a fruit bowl. 2 pieces of fruit are selected at random. Find the probability that the following are selected. So first, 2 kiwi fruits. And next, 2 different pieces of fruit. Oh, and sorry, for the last question, I just realized the answers shouldn't be just 3 and 15, since we have to find the probability. So we actually have to divide this by 20 to get the real probability. So just make a note of that, because 20 is of course the length of the universal set. Anyways, back to this. This should say kiwi. Okay, so the probability that we select 1 kiwi fruit is 3/9, because we have 9 fruits in total. But the thing is, sorry, I'm just looking at the previous question and the book is wrong, because the book says, how is the probability over 15 when you have 20 students? Sorry about that. Yeah, the book is wrong. These should be the correct answers, but I don't think I've read the question wrong, so I think this should be correct. Anyways, back to this question. So we have 3/9, but the probability that we're selecting the second kiwi fruit is only 2/8, since we've already pulled out one of the fruits. So of course we can simplify this to 1/3 times 1/4. So the probability should be equal to 1/12 for selecting 2 kiwi fruits in a row. Now the probability that we select 2 different pieces of fruit, we need to take 2 cases. So the first one is we select the kiwi fruit first, 3/9 times 6/8, which is 1/3 times 3/4, which is equal to this is 3/1/4. And we need to multiply this by 2, since we can also select the orange first and then the kiwi. So we have 1/4 times 1/2 times 2 is equal to 1/2. So that is the correct answer here. Okay. On to the next question. And the next question is, the events A and B are such that the probability of A is equal to 0.3, the probability of B is equal to 0.5, and the probability of the intersection I don't have an intersection key. What can I use as an intersection? Is equal to 0.2. So we need to find these following probabilities. So we need to find the probability of A union B, the probability of B intersection A prime, and the probability of P A prime intersection B prime. Okay, so probability of A is 0.3, probability of B is 0.5, probability of the intersection is 0.2. Okay, interesting. So first we need to find the probability of A union B. And we know that this probability A union B is equal to the probability of A plus the probability of B minus the probability of A intersection B. Since we have all of those values, that's equal to 0.3 plus 0.5 minus 0.2, which is equal to 0.6. So this is 0.6. Okay, next, probability of B intersection A prime. So, A union B is equal to 0.6. So the thing is, because we have the probability of A intersection B is equal to 0.2, and the probability of B is equal to 0.5, it follows that the probability of A prime intersection B, which is all of the elements that are not in A, is equal to 0.5, the probability of B, minus the intersection with the other set. So this is equal to 0.5 minus 0.2, which is equal to 0.3. Okay? And finally, the probability of A prime intersection B prime, well, we can use the fact that we know that we know that probability of B intersection A prime is equal to 0.3. And so it follows if the probability of A prime is equal to 1 minus probability of A, which is equal to 0.7, then the probability of A prime intersection B prime must be equal to 0.7 minus 0.3, which is equal to 0.4. So that is the answer. Nice. Okay, on to the final question, where we have the following sets. So we have U is equal to the set of X is equal to a positive integer, and X is less than or equal to 3. The A is a set of X is part of U, and X is a multiple of 3, so X modulo 3 is equal to 0. And finally, B is equal to X is part of U, and X is a multiple of 5. So we need to use a Venn diagram to represent this information and then find the following probabilities. So, well, okay, what numbers are actually part of U? Well, since we have the positive integers, this is going to be 1, 2, and 3, I think. Here, multiples of 3 is of course just 3. And this here is actually the empty set, since we don't have anything here that's divisible by 5. So if we represent this on a Venn diagram, this looks like just this. So we have 2, 1, and then 3 in the middle. So yeah, it's kind of sad Venn diagram. And so finally, we need to find the probability of A and the probability of B. So the probability of A is simply equal to 1 1/3, since there are 3 elements in the universal set, only 1 in A. And the probability of B is equal to 0, since there are no elements in B. So yeah, that was all for the speedrun. I hope you enjoyed, and I hope to see you in the next one. See you then.